Hey everybody, welcome back. Sorry I jumped the gun a bit there. I forgot that we were doing some word problems with 8.1. We're going to apply and model some of the systems of equations based on a word problem. Alright, this is a pretty neat question. It says, engineers use vertical curves to improve the comfort and safety of roadways. Vertical curves are parabolic in shape and are used for transitions from one straight grade to another. Each grade line is a tangent to the curve. So that's the tangent curve I mentioned before. So what does it mean for each grade line to be tangent to a curve? There are several vertical curves on the Trans-Canada Highway through the Rocky Mountains. To construct the vertical curve, surveyors lay out a grid system and mark the location for the beginning of a curve and the end of a curve. So suppose surveyors model the first grade line for a section of the road with the linear line y equals. So that's this one here. You see the negative slope. This is where you're seeing on my mouse. This is this part here, or the dotted part here. They're showing two parts, right? Obviously, you can have a road that goes down and all the way up. You got to obviously slightly gradually make that turn, and they do that, well, like I mentioned, with two linear lines and a quadratic going through them, right? Touching them. That's the tangent comes in. So the second grade line, this one here with positive slope, that's this part here, that's given by y equals 0.09x plus 2.35. And then you got the parabolic curve, which is the quadratic equation, y equals 0.005x squared plus 2.8. And that's where the road makes a nice road, really nice and smooth, transitioning one to the other, right? So right here, I've taken the three equations that they've provided me in the word problem. I've set them equal to y1, y2, y3 because we're going to do this on our graphing calculators or using graphing technology. So I've used Desmos here. Desmos was pretty neat. So the first one equation you see right here, the blue going down, right? It's decreasing from left to right, so that would be y1. Then obviously the second linear line, the one that's increasing from left to right, that would be y2. And then obviously the quadratic that's curved, that is y3. So I've done that in the Desmos program, and then I've found the two intersection points here on your curve. Okay, I'll do that on your graphing calculator just so you can see that. All right, so we got y equals, so we put in the clear those previous curves. All right, and we put y equals. The first one is the first linear. That's the one that's decreasing. It's negative 0.06x plus 2.6. And we got y2 is equal to that 0.09x, or just decimal 0.09x, the same thing. It's equal to plus 2.35, and then our quadratic, which is 0. Oh, there's it again. Not that it matters. 0.0045. As long as there's zeros here, that one doesn't make a difference. X squared plus 2.8. And then we're going to graph. Hard to see here with the window the way it is, so I'm going to check this window just so we can see it. That's why I like Desmos. It's easy, zoom in, zoom out. But obviously we don't need much up here, much down here, so my y, obviously I can just make this negative 1 because I'm never underneath. And then I can make this one here, it goes as high as 3, and like I can go with 4 here, and it's more than enough. And the y, the x I'll need to be left alone because we go to almost negative 7, negative 10, so I'm actually going to make this one a little bit bigger. I'm going to make it negative 12. I'll make this negative 8 because again I know where the intersection point there. So that's a little better. Still not great. Don't need this part, so I'm actually going to change my window again for my y min to be 2, and that's a little better, right? So you just got to play with your window. So I'm looking for this intersection point here and this one here. Hard to see, but second function calc, intersection. So we're going to first curve. Again, you're just going to go all the way up to the blue. We're not worried about where the red and blue intersect, the two linear lines. So enter, 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 and we get 1.6. That's and 2.5. So that was here. Actually, I jumped to the blue curve by mistake. So let's go back. So I didn't see that it was on the wrong curve. My bad. But that's no. It's an easy fix. Intersection point. Try this again. So we're on the blue curve. We want the blue curve. Enter. Second curve. It jumped down to here. It looked black. I think that's might have what confused me. I want it all black, right? Because I want to get up to this curve. Hit enter. And enter for a third time. And I get my negative 6.6 repeated in 3. Right? So on your page, that's where you're seeing the graph that you see. I think I've already graphed it for you, just so you have a nice clear graph. Negative 6.6 repeated, which is right here, 3. I know it's 3 decimal points and zeros and 6, but again, it's just pixelating in the graph. Do the same thing here, second function calc, intersection point, alright, first curve. Remember, we don't want to be on the blue, so we got to jump down to the red, so down, and you're going to keep going right, and enter, and it's all black, so it did jump up to the second black, the quadratic, which we're interested in. Enter for the third time. It is 10 and 3.5, which you clearly see on your page that I did with the Desmos program. Okay, so then we'll go back, and again, you guys have that on your page. There they are, the 2 intersection points. Determine the coordinates. We did that to the nearest hundredth. So I have 2 places after the decimal, so negative. We know it's negative 6 2/3, right? Which would be negative 20/3. But you can put it to 2. It says rounded, so that's fine. So negative 6 2/3, 3, and 10 and 2.5. So interpret each point of intersection. These indicate that the vertical curve starts at this location on the surveyor's grid and ends in this location. So the surveyor has their grid, and they know when to put them, where to start to have the curves and the grade intersect and start bringing your road. Right, so you can't have your road here like in the first diagram that you see here, because obviously the car is going to smash its front end. So we need to gradually get to the second part of the curve, and we do that through a quadratic. So it's pretty interesting how the surveyors do similar things like this. It's a neat career, for sure. Let's look at the second example. Example 2 says a flare shot up in the air. The path of the flare is modeled by the equation y equals negative 0.096. We know it opens downward. It's in vertex form, so we know the vertex is 25 and 60. In this equation, y is the height of the flare and x is the horizontal distance where it was shot. The telescope is placed in the same spot from where the flare was shot. The line of sight from the telescope is modeled by the equation 8x minus 10y equals negative 15. So we know this is in this is a linear equation. It's not in y equals mx plus b form. So you'll notice I've changed it into y equals mx plus b form. So I've subtracted the 8x from both sides. I've divided by negative 10 on both sides. So it's all negative, so everything's going to be ends up being positive here. The 15, that should be positive 1.5. I'm sorry, so that obviously should have been, when I divided, that should have been a plus, my bad, and that obviously would have made that a plus. I think my graph's fine yet. It's obviously plus. I just had to, I forgot the negative, right? Negative 5 by negative is positive. Negative 8 divided by negative 10 simplifies to 4/5. Negative 15 divided by negative 10 simplifies to positive 3/2. Or you can change it to decimal because those are terminating decimals. So y1 is one of the equations. That's the linear, the black line here. y2 is the second equation. That's the blue. Again, I did this on Desmos. I'll do it on your graphing calculator for you. And you get the 2 intersection points, and what do they mean? 2 solutions indicate the 2 horizontal vertical heights. Horizontal is x, vertical is y. That the flares can be different. So again, this is a sketch you need. You don't need this to be perfect. This is Desmos that I found just to get the points you have here. You can do a quick sketch. It doesn't have to be perfect as long as your sketch has the first quadrant with the points indicated. Okay? So I'm going to do this for you in the graphing calculator, of course. So again, we do y equals. We're going to clear our graphs from our previous example. The first one is going to be decimal 8x. Let me open 0 just so you see it. 0.8, actually that was 4/5 plus 3/2, which is 1.5. The second was a quadratic, which was given at negative 0.096, bracket x minus 25, close bracket, all squared, plus 60. So the vertex is 25 and 60, so we're obviously going to have to open that window up quite a bit. I like to show a little bit of negative, so I'll make it negative 5. It went up to 60 and 25, so it's going to come back down. So my x, I'm going to try 50 as my x. I'll scale it at 10 just so it's not too busy. My y min, we're going up to 60, so I'll make this negative 10 just so we can see some of the graph. This is going up at least 60, so I'll make it 60. Not going to pass the intersection point. To scale, I'll make it 10 so it's not too busy. And we'll graph these. And we have this beautiful graph. So you only need to do the first quadrant, these two intersection points. So all you need is a linear line straight with a ruler, quadratic going through. Again, this is a sketch. Second function calc, intersection point. Obviously got to go down here to get it close. So it's flow curve, first curve, enter, right curve, enter, enter. Intersection point is decimal 378, 1.803. Second function calc, do the same thing. Intersection point all the way here. And we're going to hit enter. First curve jump red, enter again. The next one is 41.288 and 34.53. Alright, and let's go back to the question here. We'll explain the meaning and what do these points mean. Like I said, these are the horizontal and vertical heights as far as can be viewed from the telescope. So hit here, go back down and see it again, right? On the way up and the way down, which makes sense. This is your line of view. You're going to see it first, right at the beginning, and then you see it again. Way down. 41.3 meters horizontally. Okay, so that's it. We're on finish up page 10. That's examples 1 and 2. I'll do examples 3 and 4 with you in the next example. And I'm going to do a little bit of algebraic too just to get in there. I know it's a graphic section, but I'm going to do that as well. Alright, see you again in the next video. We'll finish off 8.1, the word problem section.